Let's take a look at a couple of examples of how to find arc length of a parametric curve. Recall that if we have x in terms of t and y in terms of t, the length of the arc that connects the curve at points A and B can be found by doing the integral from A to B of the square root of the square of dx dt plus the square of dy dt dt. And this is the formula we're going to use as we walk through our examples. You will want to have your graphing calculator on hand, as we will be using those to evaluate our integrals. In this first example, we're trying to find the arc length of the parametrically defined curve x equals t squared, y equals 1/3 t cubed over the interval 0 to 1. Let's start by finding dx dt and dy dt. Dx dt simply is 2t, while dy dt simply is t squared. As we set up to find our arc length, we'll have the integral from 0 to 1 of the square root of 2t, the quantity squared, plus t squared, the quantity squared, dt. We can go ahead and simplify those before we go ahead and evaluate this in our calculators. Now, as we evaluate this in our calculators, we are going to remain in regular function mode, and we'll simply use x's instead of t's. Frankly, the calculator does not care what the variable of integration is. It will do an integral as it knows how to do. So let's go ahead and take a look at doing this on our graphing calculator. We'll simply bring up Math 9 on our quit screen, and we're going to do the integral from 0 to 1 of the square root of 4t squared, and we'll call it an x instead, plus, now we had t to the fourth, we're just going to do x to the fourth, and then we'll have our dx as our differential. And you should get approximately 1.060 as your answer. Now, another way to do this is if you find these derivatives are a little bit too complicated to find and maybe to type into your calculator, another alternative is to go under y equals, and under there we're going to put that which we were given as x of t and y of t from the parametric equation. We're going to put under y1 that which we had for x of t, but we're just going to call it x squared instead of t squared. And under y2, we're going to have that which we were given to be y of t, but we're going to use x's as we type that in. So we'll have 1/3 x raised to the third. And again, the reason that we can do this, basically substitute x's in terms of the t's, is the calculator does not care what the variable of integration is. We're going to go back to our quit screen and then use some of our other graphing calculator features to pull up, to tell the calculator to do the derivatives of these equations. And you'll notice that we get the exact same answer in the end. So we're going to bring up Math 9 again, our integral from 0 to 1 of the square root. Now this is where we'd want to have dx dt. So we need to tell the calculator to take the derivative of that which we have under y1. So if you start your parentheses, then we're going to pull up Math 8, and we're going to tell the calculator to do the derivative of that which we have under y1, and that will be over all x's. And then don't forget to use your right arrow to scoot your parenthesis out. And then we're going to square that quantity. So that which you see there is dx dt, the quantity squared. Now we're going to do the same thing for the y's. So start your parentheses, and then we have Math 8. And now we need the derivative of that which we had under y2, again across all x's. Use your right arrow to scoot your parenthesis out and square that. So it looks like that. And then we have to go out there and make sure we include our differential. So a little bit more typing, But if by chance you were given equations that the derivatives were a little bit too difficult to perhaps find by hand and type in, this would be a viable option. And when you hit enter, you'll notice you get the exact same answer. Let's look at another example. Here we're trying to find the arc length of the parametrically defined curve x equals cosine 3 theta, y equals sine 3 theta over the interval 0 to pi. Now you'll notice here we have thetas instead of t's, so we are going to be finding dx d theta and then also dy d theta. So dx d theta would simply be negative 3 sine of 3 theta, and dy d theta would be 3 cosine 3 theta. So as we set up to find our arc length, we're doing the integral from 0 to pi and square root, and we need to square dx d theta and then add that to the square of dy d theta, and then of course our differential is d theta as well. So you could type it in exactly like this if you'd like in your calculator, or you could use that method that we just had that we've already typed in and allow the calculator to find the derivatives for you. So let's perhaps do that. Since we already have all this typed in, let's take advantage of that. Let's go under y equals. Let's clear out that which we have there. And under y1, we're going to type in that which we were given as x of theta. So that was cosine of 3 theta. Now instead of theta, though, we're going to use x. The y2 is going to be that which we had as y of theta, which was sine of 3 theta, but we are going to type it in as sine of 3x. So if we come back to our quit screen, remember that you can quickly copy and paste if you have an updated TI-84 as I have here. If you use your up arrow, I'm going to go up and highlight that long integral we typed in. Just hit enter and notice it copies it down here. Now we do have to backtrack with your left arrow because we need to change those limits of integration. But I think that beats typing all this all over again. There we go. So we just need to change that to a pi. And then if you hit enter, there's your answer right away. So if you do have several of these to do by chance, it might be worth it to set up your basic integral for the arc length like this, and then just swap out what you have under y1 and y2 each time. Of course, you'll have to be documenting on paper what you did. If the derivatives are too difficult to find, it is sufficient to simply write the arc length formula as, dx dt the quantity squared plus dy dt the quantity squared, and just sort of assume the reader knows that you'd be finding those derivatives. So our answer for this one was 9.425.